Hello, my name's Thanom Shaw and I'm from the University of New South Wales. Today we're going to be looking at some problems from Chapter 3 of the Math 1131 Algebra course. So here we're looking at question 8, which is asking us to use the quadratic formula to find some complex roots of polynomials. And we'll be doing part B and part E. So in part B, we just have a quadratic, z squared plus 2z plus 3. We're trying to find the complex roots. That means we're trying to solve z squared plus 2z plus 3 equals 0. And the quadratic formula, we can use the quadratic formula to solve this as they've told us to do. So z will equal minus b plus or minus the square root of b squared minus 4ac all over 2a. So we're just substituting into the quadratic formula. You can complete the square to solve this quadratic. You don't have to use the quadratic formula here if you don't want to. But if we simplify here, we'll get minus 2 plus or minus the square root. Now here we'll have 4 minus 12, so that's negative 8 all over 2. Now, the square root of minus 8 isn't a real number. We can't square root negatives to get a real number, but it is a complex number and we can simplify it. So the square root of minus 8 is the square root of 8 times the square root of minus 1. Square root of minus 1 is just I, and the square root of 8 simplifies to 2 root 2. So here we have 2 root 2 for the square root of 8, and we have I for the square root of minus 1. So we're just simplifying here all over 2. So this gives us, dividing everything by 2 here, minus 1 plus or minus the square root of 2i. So these are the complex roots of this quadratic here, right? So therefore, minus 1 plus root 2i, minus 1 minus root 2i are the complex roots of z squared plus 2z plus 3. Okay, so that's the answer to our question, but there's a couple of things that we should notice here. The first thing we should notice is that the roots, so these roots here, are a complex conjugate pair. Okay, this is minus 1 plus square root 2i. This is minus 1 subtract square root 2i. So these are complex conjugates here, right? That will always happen when you have real coefficients there. Okay, so these come in conjugate pairs. Also, we should notice the sum of the roots. So if I add these two roots together here, minus 1 add minus 1 gives me minus 2. And plus root 2i minus root 2i gives me no imaginary part at all. So the sum of the roots is minus 2. Okay? First of all, it's real. Okay? The imaginary parts went away. They added to 0. And notice it equals minus b on a, right? We know the sum of the roots should be minus the coefficient here divided by the coefficient here. So that should be what we expect. Lastly, the product of the roots, I should put an is there, is, so if we multiply these roots here, we actually have a difference of 2 squares. We have minus 1, because they're in complex conjugates, it's minus 1 plus root 2i, minus 1 minus root 2i. We can expand, it's a difference of 2 squares. So it's minus 1 squared, which is 1, subtract root 2i all squared. So that's 1 minus 2i squared, or 1 plus 2, which is 3. Okay, so I'm just running out of room, so I'm not putting the working, but when you multiply these out, you will get 3. So again, this is real. Okay, the imaginary parts went away because it ended up being a difference of two squares, and furthermore, it equals C on A. It should be what we expect. So this polynomial here, 3 divided by 1, right, is the product of the roots. So your answer is here. But these other facts that I've written down the bottom are important things to realise. Going on to part E, we don't have a quadratic here, we have a quartic, but this quartic is really a quadratic in disguise. Okay, this quartic really looks like a z squared being squared, 5 lots of a z squared plus a 4. Okay, now we're trying to find the roots of these, so we're trying to solve this equals 0. Now you could use the quadratic formula to solve this, but we can actually factorize it because I can find two numbers that multiply to 4 and add to 5. They're 4 and 1. So this actually factorizes, and that turns out to be much easier, I think. So let's factorize it into z squared plus 1, z squared plus 4 is equal to 0. You can always double check that's correct. This expands to z to the 4 plus 4z squared plus 1z squared is 5z squared plus 4 gives me 4. Okay. Now, I could say from this point, if these two things multiply to give 0, z squared plus 1 is 0, or z squared is minus 1, z squared plus 4 is 0, or z squared is minus 4. I can solve it like that, but I'm actually going to factorize here just because I can. So z squared plus 1 is actually z squared minus I squared. I squared is minus 1, so minus I squared is plus 1. Similarly, z squared plus 4 is z squared minus 4i squared. Okay, and the reason I want to do that is because now z squared minus I squared is a difference of two squares, and I can factorize it. So this gives me z minus I times z plus I. And the second factor here gives me z minus 2i, z plus 2i. Okay, and from here I can write down all my roots. So 4 things multiply to give 0. One of them's got to be 0. So either z equals I, or minus I, or 2i, or minus 2i. Notice again, they come in complex conjugate pairs. I and minus I are a pair. 2i and minus 2i are a pair, right? So these, let's just write this, finish the sentence here, are the complex roots of z to the 4 plus 5z squared plus 4. So here we had a quartic, but because it was a quadratic in disguise, we could factorize it easily, although you could use the quadratic formula here. And because these were nice special quadratics, we could factorize them again easily. So we didn't actually have to use the quadratic formula in that question. And that's the end of those parts for question 8.